All right, guys, welcome back. Hopefully, this will be the last time that the last video for this series. I'll be able to start really cranking out the stuff for Pulse. We've kind of got a plan going together. Hopefully, we'll be able to get some more details out to you guys here in the next couple of weeks. But once you guys are through with this, if you haven't got your homework in yet, get that in so I can release the test out to you so we can get this all taken care of. So then all we got is lab time left. If you got any questions, drop me a line, do whatever you got to do to get a hold of me, and we'll get this stuff figured out. So without further ado, let's go ahead and get cracking. Now, have your Chapter 25 PowerPoint brought up, kind of walk through this with you. You can have me playing in the background here, go through. We're going to jump ahead all the way to slide 44 first because we got through all the stuff last time over different types of discontinuities, and now we're going to get into some different testing methods. So first testing method we're going to get into is destructive testing. What is destructive testing? Well, another word for that is mechanical testing. So what does that mean? Well, if we're going to, this is the only actual testing that actually happens. It means we're going to take something and we're going to make it fail. We're going to twist it, pull it, crush it, hit it, bend it, do whatever the heck it's going to take to make that thing fail. And it may or may, well, take it back, may or may not fail depending on the type of test that we're doing. Some tests will go all the way to failure. Nick brake test, we'll talk about that in a little bit. Absolutely must have a failure for that. Ultimate tensile strength will be a failure. There'll be other pressure test failures. If you're building pressure vessels, they're going to pull one off to the side, they're going to take it out, they're going to pump it full of usually air, but sometimes they'll pump it full of pressure until it blows, and you got to meet at least a 3 or 6 times your working limit safety factor. But the reason that we do this is the exact same reason you guys that we do destructive testing is the exact same reason that we do our bend test and our brake test, which are what type of testing? Destructive testing. You can't hide anything from it. The non-destructive inspection, that's why we're going to be using that term. The term that you're going to see in the book is non-destructive testing, but we're not really testing anything. We're just inspecting it. Well, the reason that it's called a mechanical test is because we are testing it. We are getting distinct results back. We are putting it through, and we know that that part was good or not. You cannot hide anything from destructive testing. Everything else has got a little bit of wiggle room in it. But this is why destructive testing trumps every other form of testing out there. This is why we do bend tests. Even after stuff has been x-rayed, it can still, a bend test will still trump an x-ray test. So moving on, next slide. So tensile testing. Well, we have a bunch of different types of strengths. We've talked about this before. We're going to talk a little bit more about this when we get into the next, into 164 and then ARC 2 in the next semester. But tensile strength, we're going to take two pieces, we're going to pull them apart like this. That's going to tell us how strong that weld is. Be a couple different types. We're going to have the weld in the middle on two pieces of base metal. We may have a round piece in the center that's going to be machined right out of the center of the strip. It's called an all-weld metal tensile test. And all these ones are going to be done for different purposes. Not all of them are going to be done the same. And because we need to see what the heat affected zone does to the strength of that. Too much heat in too small of an area will give us a much more brittle weld than say, well, this is where we get into. Hot and fast is always going to be stronger than cold and slow. Cold and slow, even though you got a lower temperature going into it, you're hanging out longer, so you end up with more joules per inch. That weld is going to be weaker when it comes to notch toughness application. We'll talk about those later. But when you do, your tensile strength will always be given in either kilopascals or pounds per square inch. What we're looking for is just how long it's going to take, how much that stretches, and what it takes to actually break it. Going on the next slide, up to 46. This is just a standard piece. This is what a round all weld metal section would look like. Don't worry about this. This is test lab stuff. This stuff we'll do a little bit of, but not something you're going to see out in the real world unless you're proving out a WPS. Dimensions, don't worry about that. Dimensions for flat weld plate, again, don't worry about that. I don't like when they tell me that there's they give you specific dimensions, because while these are true for the D11, they don't necessarily match all the different codes. Depending on the type of material that we have for strength, whether we're looking for creep, elongation, things like that, we may have slightly different slightly different specimen sizes. So even though the book goes and says, and the slides go and say that, yep, these are your sizes, no, it changes with different codes that whatever we're trying to be working towards. So next one's fatigue testing. What fatigue testing is, do it. We're going to bend it, see how long it takes to get weak, see how long it takes to fail. Some of this stuff is going to be done really, really fast. Some of it's going to be done slow. Some of it, we're going to take it. They're going to have to do a bunch of measurements, do some real fancy math on it, and say that, okay, we ran it through 100,000 cycles, and this is how much it weakened. So we're going to say that it's going to take 2 million cycles to failure. And I said there's going to be math involved to figure that stuff out. This is something that's really important, though, when you're figuring out things with dynamic loads. Remember that every joint on a bridge is considered to be dynamically loaded. So this would be one application of it. The other things that this would be for would be like the frame rails on a car or truck. How those are all flexing and twisting. And this is why whenever you're dealing with that stuff, you should never, ever weld on it, because you are changing the mechanical properties of it. And they do have a lot of spring, a lot of twist to them. And if it can't do that, well, it's going to crack, it's going to fail, and if you welded on it after that or before that failed, you could be in trouble. So boss says do it, and it's his liability. That's one thing. I'd say, hey, I don't feel comfortable with it, but for the most part, if it's your idea, don't do it. Shear strength. Well, shear strength is we're going to take two pieces, break it like that. Just that simple. We have see how long, what it takes to actually get them to break or shear. Sometimes this is done for mechanical testing. Sometimes this is done for, or not mechanical testing, but sometimes this is done with impact testing. And it's figured out, again, in pounds per square inch. How much pressure over how much area did it take to actually get that to shear? Again, more different types of tests. Not worried about, not worried about, not worried about. All right. Going up to slide 54. So talking about testing butt joints, a couple different ways we're going to do this. Now, some of these are going to be field expedient. Some of these are going to be normal types of tests. First off, nick brake test. Nick brake test is going to be always required. You can remember this because I know you're going to see it on the test. But a nick brake test is always required whenever you're doing any test to API 1104. That weld must be ruptured, and we need to look at the internal structure of it. So a nick brake test, what we're going to do, and go on to slide 55, is we're going to take our butt joint, we're going to actually saw around it, we're going to bend it over till it actually fractures, and we need to see the inside of that joint. Okay, we're going to be looking for inclusions. We're going to be looking for how it breaks, things like that. But it's always going to be, nick brake test will always be required for API 1104, and it'll always be required for that weld to be ruptured. We're going to keep beating on this sucker until it actually breaks, no matter what happens. And to show kind of how that's going on 56. Okay, guided bend test, page 50, slide 57. You guys do this. We do this all day, every day on your V grooves. You guys have seen this done. Nothing too fancy here. The only thing that we do here is we change it around a little bit. If we had stronger or weaker materials, we change that center arbor that we're wrapping that around with our bend jig. But you guys know the details about this. You've seen it. You've done it. We don't need to spend a whole lot of time going over that. So we're going to jump through. It shows different types of jigs. Then we're going to get into free bend test, What a free bend test is, and we can jump all the way down to page or slide 64 for this. What a free bend test is we're going to take that, and this is a field expedient test. We're going to take it and we're going to bend it around a certain radius. Instead of having something we know the exact size of and have a big fancy jig, we're going to go and stick it in maybe a vise, hammer it over. We're going to put a piece of round stock in it, press down with it, do something like that. This is just proving out, saying that, yep, this works, let's try this, rather than just praying that it's actually working. Like I said, you want to keep these specimens. If you do end up doing something like this, it's great for determining the strength of material, make sure the stuff's going to match. Let's say you have an unknown type of material you're supposed to be welding on. You want to make sure that your settings are right. If something just don't feel right, take a piece of scrap of it, weld it up, do a free bend test, and see what happens. If it passes through that, you're probably okay. Doesn't pass through that, that's definitely an indication we need to start looking into this more. Find a WPS, find out exactly what sort of tests were done with this. If it was pre-qualified, figure out who pre-qualified it, by what type of materials we were doing on the WPS, because a pre-qualified WPS, if it's using the right materials, should never fail. If it does fail, it's almost always going to be the welder's fault. If we go into, but you may end up having a WPS where the materials don't match. They're supposed to be welding this material over here. Well, this was cheaper, and somebody bought it not knowing the difference in the specs. Maybe this had a slightly different alloy, but now we're having problems with stuff working. And a nick brake test would be a quick and easy way to figure out that, hey, we got something wrong. Or excuse me, not a nick brake test, but a free bend test. Alternate bend test, same thing. Bending it one way, bending it another way. Going on to slide 66. This is going to be your fillet weld brake test. Now we do a bunch of these. We're going to take your fillet weld, you guys have seen it, flatten it out, blow it, take a good look through it. We're going to be looking at that time for inclusions. We're going to be looking for penetration. We're going to be looking for slag down the root, things like that. Quick, easy, dirty, but it works. It's easy to prove out in a hurry and prove that this is going to work. Testing by etching. This is either going to be a micro etch or a macro etch. And what this is going to do is we're going to take that weld, we're going to polish it up, and we want to get it real close, as close to a mirror shine as we possibly can. Then we're going to dip it in acid. What that acid is going to do is eat away basically the softer spots in between the grains at the grain boundaries and bring that up through. A couple different types of acids we can use. I don't care if you remember what they are, because certain codes and different materials and different codes are going to require different ones. So yeah, hydrochloric acid is probably the most common, but there are others. But at this point, what we're going to do is, after we get done with etching that, we want to take a look at it. We want to go and see what happens to that grain structure. And we have charts that we're going to be using to compare that to see what size the grains are. This is going to give us an idea on what the nick brake test is going to look like. It's going to bring out the weld metal. It's going to bring out the base metal. It's going to bring out the heat affected zone. And we're going to be able to really, really see well what's going on with these inside that weld with the grain boundaries. Yep, skip that. Impact testing. Charpy V-notch test. We're going to do here, and these are always going to be required for bridges. Every single bridge procedure has to be qualified to a Charpy V-notch test. What we do is we take a piece of steel, they machine it down to a very specific size, and we cut a notch in it, again, very specific size, and they freeze it. Then I have to get it to a specific temperature. Then what the Charpy test is, just a big hammer comes up, hits that, knocks that piece off at the notch, and then continues to swing through. Well, we know that with how much energy we have when we start, because we know how heavy the hammer is, how high it is, and it's going to hit that notch at peak. Well, and then we're going to see how high it comes up. The amount of energy that it takes to knock that piece off is going to slow down how high that hammer comes back up. And then we can record that. The amount of energy that it takes for that is going to depend. And that energy going into that, basically, it acts just like heat. And you'll actually see a heat-affected zone around it. The frost will melt right around that impact point. Just remember that all energy can be translated into heat in one way, shape, or form. And it's cool to see. And there's some videos out there if you want to go check them out. I'm not going to require you guys to look at them. Charpy tests are cool. I want to get a Charpy tester at some point in time. Cheap ones I've been able to find that someone would come certify start at about $40,000. So guys, if you want to make a donation to the program, I'd greatly appreciate it. But like I said, it's on the list. We'll see what happens. So then we're going to get into NDT, and this is why I say NDT stands for non-destructive testing. We are not testing anything at this point. We are inspecting. NDT is no longer the standard term. It is non-destructive inspection. So moving on to slide 71. This is our most common type of inspection is what? Visual. Mark 1 eyeball. Mark 1 eyeball to catch a lot of stuff. Every code is going to have a set of visual criteria. Before we do anything else, because, you know, how expensive is it to, like I said, have that Mark 1 eyeball on a weld? You know, depending on how much you're paying your inspector, it's still going to be cheaper than bringing somebody in and having to use any of the other type of inspection. So before we do anything else, everything's got to pass a visual. If it doesn't pass the visual, there's no point in going on. Every code's going to have visual requirements. And then it's going to have other forms of inspection that are going to be over and above that. Everything that we do with visual inspection, though, or any of these types of inspections has limitations. Primary limitation with visual inspection is we can't see inside that weld. So anything that is down under the surface, it's there. We have no idea it's there. Now, there's a few things that if you really, really know what you're looking for, you're going to see some indications of there. These are things that inspectors develop over time. We're looking for fish eyes. We're looking for just strange ripples in the type of the bead, things like that. But this is also why certain types of welds have hold points, where when you're doing a multi-pass weld, there's an automatic hold point for your root pass. So if you don't get your root pass in right, and we're going to stop because you can bury it and we'll never be able to see it. Have had to tell somebody on a big project to, dig that back out. Made them very, very unhappy with me, but they were told that, put the root in and wait. And, well, they didn't wait. And they wanted me to sign off on it. I refused because, well, this is what the code says. We dug it back out and that root was crap anyway. Someone was trying to hide that they were a garbage weld. And so, there's a reason those hold points exist. So next one that you guys see, this is one you guys are doing when you're doing your multi-pass weld. We're up to slide 75. This is penetrant inspection. It means that we're going to spray it down with dye. We're going to clean it up, usually wipe it in one direction. Then we're going to put a revealer on top of there. Now this is going to be probably your second most common test you see out in the real world because it's cheap, it's really, really accurate, it's easy to identify where we have problems. You're going to see this used all over the place. This is used very, very commonly on food inspection surfaces because even if we have cracks that are so small we can't see them with the naked eye, that's going to dye penetrator will pull them out. If we're looking for very, very, very fine cracks, even finer than what we can see that way, then we're going to use a UV reactive dye. So it's going to go in, we're going to clean it off, and we're going to hit it with a revealer and inspect it with a black light. And those will pull up cracks that are down into the less than 1/1000th of an inch. And if there's a crack there, it will find it. It's good, it's fast, it's really one of the easiest ones to learn how to use, one of the easiest ones to learn to become certified in. But issues with it is, again, we can only inspect things on the surface. Becomes really hard to inspect things with different complex geometries, and it's kind of a pain in the butt if you got to go and check large areas with it. So moving on. Okay, mag particle inspection. There's videos again out there on YouTube you can check into. Now we're up to slide 78. So what you got with mag particle is we're going to take a piece, charge it with a magnet, and with the magnet hold there, then blow magnetic powder onto there. If we have a nice smooth piece, the magnetic flux line is moving smoothly, that powder will come out pretty evenly. If we have cracks though, what happens is those magnetic flux lines can't jump the crack. So they bend around it. As those lines bend, they push on each other. It actually concentrates the magnetic forces right there, which will cause this dust to accumulate right at the crack. Advantages for mag particle, again, fast, very, very fast. Equipment's cheap. Can be used on a lot of different types of materials. It can even be used on painted materials. We can find flaws in materials if you've got the right type of material and the right type of dust. We can find this stuff down to about 1/8 of an inch. So we can get, now we're getting down not well into the weld, but we can at least get down below the surface. Fast, dirty. Well, like I said, it's really fast, works very, very well. Limitations on this. First off, as I said, we're still stuck on the surface. We can't really look at the inside of that weld. We can get down about 1/8 of an inch, and that's about it. Takes a very, very experienced inspector to be able to find discontinuities at that depth. Other thing is, this is only good for magnetic material. We can't do this on austenitic stainless steel. We can't do this on aluminum. We can't do this on most non-ferruses. If it will not, if it's not a magnetic material, we can't use this. The other problem is this is dirty. You got powder everywhere, so somebody's got to come back in and clean that up after it's been inspected. So there is a little bit of cleanup involved with it. But very, very common out on construction projects. Anytime we're dealing with steel, it's a pretty decent process. Couple different shies that. Okay, RT, moving on to slide 80. RT is otherwise known as X-ray, radiographic inspection. Another form of that is going to be gamma ray inspection. Biggest difference between gamma ray and X-ray is the amount of exposure time and the amount of energy that you're being exposed to. Both of these right now, they're nice. The reason that a lot of places still use these is because it provides a permanent record of that weld. In places like pipelines, radical new construction techniques, skyscrapers, things like that, they will maintain the record of these welds as long as that building is in existence. Things about RT works out. RT will now we're starting to actually look into the weld. We can see what's on the inside of it. Problems with it though is, first off, especially after September 11th attacks, moving radiological materials across the country became a real pain. It's better. It's better than it was, but from about 2001 to about 2006, good freaking luck. Trying to move an X-ray source, trying to move a gamma source, was a real, yeah, you better have all your papers in line. Other thing with this is it does require a relative, the pieces are expensive, the receiving end's expensive, your films are expensive. It adds up in a hurry. On a lot of big projects, what they'll do is you have 100% visual inspection and critical welds will be called out 100% for inspection. And then everything after that's going to be, there'll be a 5 or 10% random on the inspector. What happens though is on those 5 or 10%, if they start finding failures, then the numbers go up and up and up and up. And then your contractor's ever doing the welding has to start eating those extra tests. But anything that's going to be a radical construction technique, new techniques, or anything that has to deal with earthquake zones, seismic zones, anything like that, it's going to be 100% X-ray. And those records, that's the reason they stick around is because once those records are done, they exist forever. And if there's ever a problem, that's the very first thing they're going on to do is pull those films. So, talk a little bit about that. And just remember, as I said in the other one, is how X-ray works is that if you have the steel or the harder spots are going to show up as white. That's why your bones show up as white in an X-ray. Everything else kind of fades away. So if looking at this slide here on 82, we're seeing voids in 1. That's telling me that you're seeing those little dark spots in there. Those are voids. That means we either got slag inside there, could be porosity, but there's holes inside that weld. Looking on the other one of that slide where we have that where it's bright white there in the center and then fades away, that's definitely an indication that we have excessive weld or excessive penetration in that spot, where the X-rays can't penetrate that one piece near as well as it can the rest of it. So there's got to be a lot more weld there. Other types of films, guys, you can look at these other slides. You're not going to be that shows a whole bunch of different stuff, but this isn't your this isn't a class teaching you guys how to interpret film. I just want you to know that they're there. You can go back and look at them at any given time if you want. NDT is a great field inside the welding world to get into, but outside of what we're doing right now. Last one we're going to get into is UT, ultrasonic. Ultrasonic is kind of really taking the place of X-ray in a lot of places, because we can get a full three-dimensional build inside that weld or inside a joint. We can go through very complicated geometries, and with the newer technologies, we can have basically GPS attached to the scan tool, so we can get make that permanent offsite record. We know exactly what was there, where it is, and we can scan around it. Multi-phase UT is really cool, but it's expensive, and it does take a lot of training to be able to use and interpret it correctly. You got to be able to get really good at geometry, which is just right angle geometry, right angle trig. Nothing super tricky. Don't let that scare you. But well, all this is doing is just like ultrasound you're seeing, we're let you do for medicine, just a little higher energy. We're putting sound waves into material, and we're seeing how it bounces back. And by interpreting how long it takes, what its deflection at, because we can actually change kind of its angles and what we see, how it hears it. We can anticipate there's problems, different spots in the weld. Leak checking. Leak checking is something real common in pressure vessels. Has to be done. What we're going to do is we're going to pump something up, see how long it takes for that pressure to come down. It's going to be measured in standard feet per second or standard meters per minute. And usually it's very, very, very small. Now, if we're looking for things that where a very small leak is a big deal, now we're going to end up, instead of doing it with just air, we may end up doing this with, say, helium. At this point, guys, you guys got to remember, everything leaks. The only question is how much. Every one of those high pressure tanks we got out there leaks a measurable amount if we want to look down into it. Helium and hydrogen, if we're going to use those for leak testing, we can actually go and see how much is actually moving through the grains of the metal. This is why storing helium and hydrogen is so tough, but it makes it perfect for checking for leaks, because we know we're going to see some. So if we charge a part to a given pressure with helium in it, pull a vacuum on the outside, we should see X amount come through there. We can calculate that out with some relatively complicated math. And I'm almost done, guys. It lets us know that we got a good test if we only see so much. We got a bad test if we see above that. If we don't see enough, then something happened with our source gas, and then we need to look at that. Any places that makes things, radiators, heat exchangers, cooling system components, anything like that, they're going to be leak tested that way. Eddy current. Eddy current is one of the more complicated types of testing out there. It's one of the few that can actually pick up the grain structure from the outside. What we're going to do is we're going to induce a magnetic field into an area, in a very, very small area, through a little bit of current, and see how it read how that current moves through the part. This isn't necessarily magnetism because it's actually picking up different types of, or it's interpreting the electrical signal, not a magnetic signal. Eddy current is awesome. It is very, very sensitive. We can actually start picking up grain structures. We can find micro cracks, and again, we can read down about 1/8 of an inch. The thing with eddy current, though, is it'll find everything, but that's the problem, is it'll find everything, and it takes a very good operator to be able to look at eddy current and pick out problems throughout the noise. I said very, very good, but it takes a lot of training to be able to do it and use it right. Hardness testing, 94, 95. We're going to see how hard something is. What we're going to do is take what's called a penetrator. We're going to push it in and see how deep it goes. That's simple. That's how we do a Rockwell or new hardness. And it's going to let us know just that, how hard our material is. Sometimes this is really, really important. Sometimes it's not. So, guys, that's the last bit for that. This is the last one for this chapter. So, get through this, get your homework in, get your weld procedure in, and I'll release this test out to you. Your weld procedure has to be done right. Don't just throw some numbers in there and hoping I'm going to take it, because not going to happen. You got any questions, shoot me an email. I'll get back to you. So, see everybody later.